Hi everyone! In this video we're going to learn about one additional method to check if a linear model is appropriate. In other words, this test will help us to confirm if the relation between variables in bivariate data is indeed a linear relation. This method consists of constructing a special graph, it's called residual plot, and then analyzing it. Let me show you how to construct a residual plot. So first of all, we're still using same bivariate data as we used in our previous example. So here we have ages and prices for various Honda Accords. And what we need to do to construct residual plot, we need to first compute predicted price predicted by a linear model. We also call it the least squares regression line, and its equation is called regression equation. We found it in the previous exercise, so I'm going to just copy it down. So it's y hat for predicted value of the response variable, negative 0.9x plus 18.4. Now, from the name of the plot, residual plot, you might guess why we need predicted values of the response variable, because residual is the name for an error that happens when we use linear model to estimate values of the response variable. And the residual is the difference between the observed value, the one that comes with the data set, and the predicted value. So we'll need to compute the predicted price for each value of the explanatory variable. In other words, to find y hat, what we'll do, we'll just plug in each value of the explanatory variable from the table for x and compute y hat. So it's negative 0.9 times 8 plus 18.4. And we already did that in the previous exercise. We know it's 11.2. And now I'm going to continue in that matter. I'm going to do one more line like that, and the rest I'll just compute on the calculator without writing them out. So that's going to be times 7, next value of the explanatory variable, plus 18.4. That's 12.1. So I plugged values of the explanatory variable into the regression equation one by one, and these are the values I obtained. Next, we're going to complete the last column, and that's the one that's called residual. So for each value of the explanatory variable, we're going to take the observed price, that's 13, the first one, and subtract the predicted price, 11.2. We can see that the predicted price is below the observed price, so that means that we underestimated. The underestimation is 18.8. By the way, these are prices in thousands of dollars, so that's 1,800. That's underestimation, and that's what we call a residual. I'll make a note here that that's another word for an error in estimation. For car age 7 years, the observed price is 9.2, so that's the actual price of an actual car, of an actual 7-year-old car. And using the regression equation, we estimated the price to be 12.1, so we overestimated in this case. So the residual, because of that, will be a negative number, negative 2.9. I continued in that matter and found the remaining residuals. And now we're ready to construct the residual plot. A residual plot looks similar to a scatter diagram, but the difference is that the vertical axis on the residual plot corresponds to residuals. Now the horizontal axis still corresponds to the explanatory variable. I already labeled the horizontal axis, and now let's label the vertical axis together. Since the vertical axis corresponds to residuals, let's look at the values that we got for residuals. So here they are in the table. As we already know, some of them are positive for underestimation and some of them are negative. That's when overestimation happens. So that means that we need to label the vertical axis in such a way that we can plot both positive and negative numbers. And this is how this is done. We're going to put 0 in the middle of the vertical axis, so 0 will be over here. And then above, we're going to place positive values, and below, we're going to place negative values. Let's look at the range of the residuals in our example. So we need to know, so that we know how far to count on the vertical axis. Looks like the smallest number is negative 2.9, so I can go down to, let's say, negative 3, and the highest value is, the highest positive value is 1.8, I think, right? So let's do numbers between, let's say, negative 3 and positive 3. And another thing that we usually do on a residual plot is that we draw a dashed line through 0. That's kind of like the border separating overestimations and underestimations. So visually, it's going to be easier to distinguish them. And now we're ready to start plotting points. Since the horizontal axis corresponds to explanatory variable and vertical axis corresponds to residuals, that means that these are the columns in the table that we have to look at to find coordinates of points that we're going to plot. So the explanatory variable is listed in the first column. So I'm going to take a value, the first value of the explanatory variable, that's 8, and I'm going to take the corresponding residual, 1.8. So the first point that I will plot will be 8, 1.8. 8 is here, and then 1.8 is about, let's say, over here. So I'll just make a note for this first point. This is 8, 1.8. Now, what's the next point? The next point is 7, negative 2.9. 7 and negative 2.9 is over here. So I'm going to continue and plot the rest of the points. So here is our residual plot. As you can see, it illustrates positive residuals that are above 0. So those are underestimations, and negative residuals, they're overestimations. How do we interpret the residual plot so that we can confirm that a linear model is an appropriate model for our given bivariate data? What we need to do is to observe a pattern of a residual plot. And if a residual plot does not show any discernible pattern, well, that's when we can say that the linear model is appropriate. So in other words, we don't want to see a pattern. And if it happens that we observe some kind of pattern, for example, most residuals are above 0. So that means that the model is constantly underestimating the response variable. Or maybe first we can see all the residuals above 0 and then below 0 and then above again. So that's kind of like a U-shaped pattern. So that's also an indication that the linear model is not appropriate for a given bivariate data. And we'll see more pictures of that. So I added a note outlining the idea of this test. So it says that if a residual plot shows a discernible pattern, then the explanatory and response variables may not be linearly related. So conclusion that we make here for our example, since there is no discernible pattern, so our residuals are all over the place, that means that we conclude or confirm that the linear model is an appropriate model for the two variables that we study in this bivariate data. Let's look at a few more pictures and examples of residual plots. In this example, we're asked to match the given scatter plots with their corresponding residual plots. So let's try that. Now, here's our first scatter plot. What can we see? What kind of model we can see here? That is an exact linear model because points of a scatter plot lie right on the line. So that is a perfect association between the two variables. Let's think in terms of residuals. In other words, let's think in terms of errors and estimations that we might make. So since all points lie on a straight line, will there be any errors when we estimate? No, we'll never have any difference between the observed value, the point of a scatter plot, and the predicted value point on a line. So since all residuals are zeros, what residual plot does this correspond to? Well, the one over here, notice how this is 0, and all the residuals are at 0. So that means that, let's make an arrow here. So this scatter plot corresponds to this residual. Let's look at the next scatter plot. Here we can see that the linear model is positioned in such way that it comes close to all the points of a scatter plot, and we have points above and below the line. So when we think in terms of residuals, some predicted values will be underestimations because points on the line would lie below the observed values, and some predicted values will be overestimations since they lie above the observed value. What do you think is the corresponding residual plot? So here we have overestimations, underestimations, and that must be the one in the middle, right? So that's going to be our guess, because as we move on to the next scatter plot, what can we see here? So that's a good example, this last picture, because notice that we have a linear model that we attempt to use to describe the relation between the two variables. And what happens is that if we compute correlation coefficient for this bivariate data, it will show the linear association, well, because all the points come close to the line, right? All of them are very close to the line, but notice that down here, observed data is above the model, so that means that model will be underestimating for lower values of the explanatory variable. In the middle here, the observed data is below the line, so it means that our predictions will be above the observed data, so we're going to be overestimating for those middle values of the explanatory variable. And at the end, again, at the higher values of the explanatory variable, we're going to be, well, looks like mostly underestimating. And this all will be reflected on the residual plot. So residual plot will shows arrows above 0 at first, and below, and then above again. And now we can see that the residual plot has this U-shaped pattern. So that's what we call the discernible pattern. And while the correlation coefficient will be misleading by showing that correlation is strong enough so that we can use linear model to describe this data, we do see that it's better described by a curve. And in this case, residual plot is the effective tool to detecting when linear model is actually not appropriate one. So first of all, that's the corresponding residual plot. And we're going to say that the discernible pattern of this residual plot confirms that the linear model is not appropriate for this bivariate data. I'll say linear model is not appropriate. And the other two residual plots, since they didn't show any discernible pattern, they confirm that the linear model is appropriate for the first two bivariate data sets.